two bodies were thrown simultaneously from the same point, one straight up and the other at an angle of theta equals 60 degrees to the horizontal. The initial velocity of each body is equal to v naught equals 25 meters per second. Neglecting the air drag, find the distance between the bodies at time t equals 1.70 seconds later. In this video, we'll solve a projectile motion problem involving two bodies thrown simultaneously from the same point with the same initial speed, but different directions. Let's establish our coordinate system with the origin at the launch point, positive x to the right, and positive y upward. We'll represent our first object thrown straight up with a red ball, and our second object thrown at 60 degrees with a blue ball. Both objects experience the same acceleration due to gravity of 9.8 meters per second squared downward. For the first body going straight up, the initial velocity is v naught equals 25 meters per second in the positive y direction. For the second body, the initial velocity is also v naught equals 25 meters per second, but at an angle of 60 degrees to the horizontal. We can break this down into components. The x component is v naught times cosine of 60 degrees, which equals 12.5 meters per second. The y component is v naught times sine of 60 degrees, which equals approximately 21.65 meters per second. Now, let's develop the position equations for each body. For the first body thrown straight up, x1 equals 0 for all time, since there's no horizontal motion. y1 equals v naught times t minus 1/2 gt squared. Substituting our values, we get y1 equals 25 times t minus 4.9 times t squared. For the second body thrown at an angle, x2 equals v2x times t, which is 12.5 times t. y2 equals v2y times t minus 1/2 gt squared. Substituting, we get y2 equals 21.65 times t minus 4.9 times t squared. Let's visualize the trajectories of both bodies. The red ball moves straight up and then back down, while the blue ball follows a parabolic path. At t equals 1.70 seconds, the first body is at this position, and the second body is at this position. The separation vector between them is shown here. Now, we'll calculate the separation vector components and find the distance. Delta x equals x2 minus x1. At t equals 1.70 seconds, x2 equals 12.5 times 1.7, which is 21.25 meters. x1 equals 0. So delta x equals 21.25 meters. Delta y equals y2 minus y1. y2 equals 21.65 times 1.7 minus 4.9 times 1.7 squared, which is 11.03 meters. y1 equals 25 times 1.7 minus 4.9 times 1.7 squared, which is 16.72 meters. So delta y equals 11.03 minus 16.72, which equals negative 5.69 meters. Now, the distance between the two bodies is the magnitude of this separation vector. Distance equals the square root of delta x squared plus delta y squared. Distance equals square root of 21.25 squared plus negative 5.69 squared, which equals square root of 451.6 plus 32.4. resulting in exactly 22.0 meters. And there we have it. The distance between the two projectiles at time t equals 1.70 seconds is 22.0 meters. This problem demonstrates how to track the motion of objects in projectile motion and calculate their relative positions.